Hello. So we'll be starting our lesson for statics of rigid bodies, and our next topic would be equilibrium of rigid body. And these are the objectives for this topic: to develop the equations of equilibrium for a rigid body. So these are just the summation of forces should be equal to zero, and summation of moments should be equal to zero as well. And to introduce the concept of the free body diagram for a rigid body. So previous lessons we already tackled free body diagram. This time we will be applying it to a rigid body, and also to show how to solve rigid body equilibrium problems using equilibrium equations. So the conditions for rigid body equilibrium is that the summation of the resultant force, or the summation of all forces, must be equal to zero, as well as its components. The summation of f of x should be equal to 0, summation of f of y should be equal to 0, and fz also should be equal to 0. And the summation of all the moments must be equal to 0. So as you can see, this is our rigid body. It's acted upon by several forces in several couple moments or moments, and what we need to do is to resolve it into a resultant force in a resultant moment acting at point O, an arbitrary point O, and the summation of these moments must be equal to 0, as well as the force. Okay, so mostly we will be doing two dimensions for the following calculations in this one. So as you can see here, we have a plane, an airplane, and this is the external forces acting on it. There is a reaction on its roller here, or its wheel, as well as the rear wheel. There is also another reaction, and we have the weight of the airplane, which is acting on its center of gravity right here. So this is an example of a free body diagram. Okay, so free body diagrams are sketch or outline shape of a body which represent it being isolated or free from its surroundings, thus a free body. Alright, you already have a background how to draw free body diagrams from our previous lessons, and now we will be looking for external reactions. So we have support reactions. So here are the general rules. So a support prevents the translation or the movement of a body in a given direction by exerting a force on the body in the opposite direction. So this is where the support reactions are. Okay, if it prevents, so remember these general rules so that you will be able to identify how many forces are acting uh, on a point on a rigid body. And number 2, the support prevents rotation. So it prevents translation and it prevents rotation of a body in a given direction by exerting a couple moment on the body opposite the direction. So let's examine some forms of external support reactions. So we have a roller, we have also a pin, and others as well. So we will see later on what are the external reactions that we should draw with our free body diagrams depending on the type of support reaction that it has. So we will just be applying the two general rules, that it should prevent translation and it should prevent rotation as well. So here is a table. This identifies how many support reactions are there depending on the type of support or type of connection. So you are free to memorize all of this, but it would be easier if you will just remember the two general rules. Number 1, it must prevent translation, and number 2, it must prevent rotation. So let's examine if this is a truss member here, and it's supported by number one, a cable. Okay, so it says here it's one unknown. This force, the reaction is a tension force. Remember, it's a tension force which acts away from the member in the direction of the cable. Okay, so if you see a cable connection, it would always have this external support reaction. Number two, a weightless link. So it's somewhat the same for a cable connection. Also one unknown, and the reaction is a force which acts along the axis of the link. Okay, so it's not just a tension force. It could also be a compressive force. Number three, a roller. So you will see a lot of roller support reactions in the preceding examples. So if you see a roller, this is also one unknown. The reaction is a force which acts perpendicular to the surface of the point of contact. So it's normal, okay? It's a normal force to the perpendicular to the surface of the point of contact. So let's try to apply our general rules here. Look at the roller. So why is there no reaction on the perpendicular to the roller, to the reaction or the normal force? Because if you have a roller, you can move on the, sideways, right? So this one is inclined here, but if you will put it in an xy axis only, so that means it doesn't prevent movement. That's why there is no support reaction. Okay, so does it also prevent rotation, our roller? No, it doesn't. That's why there is no couple moment as a support reaction. Okay, so here are other types. We also have here a rocker connection. So this is usually applied when there is expected vibration, I think. So there is also one unknown. The reaction force is perpendicular to the surface of the point of contact. So it's somehow the same as roller connection. Okay, so if you have a rocker connection, you can also move sideways. That's why there is no reaction perpendicular to it. The same as smooth contact. Okay, you can also move sideways. That's why there is no support reaction. The only support reaction would be where the translation is prevented, and that is normal to the surface. So if you have a roller or pin in a confined smooth slot, this is your reaction force, either compression or tension. If you have a member pin connected to collar or smooth rod, this is your reaction force. Okay, now we go to a smooth pin or hinge. So this is also one of the common connections that you will see in our next problems. As you can see here, now it's different. There are two unknowns. The reactions are two components of force. So why is that? We said if it's pin connected, we said that if there is a support reaction when translation is prevented on the direction of motion. So if you have a pin connection, can you move it along X? No, it's prevented. That's why there's a support reaction. Can you move it along Y? No as well. That's why there is a support reaction. Okay, so I hope you can see the difference of the smooth pin or hinge connection to like a roller connection or a rocker connection. That's why we have this support reaction along F, X, and Y. So we also have a member fixed connected to collar or smooth rod. So here, it can move sideways, but it cannot move along this axis. That's why there's a support reaction, and you cannot also rotate it. That's why there is a reaction which is a couple moment. So there are also two unknowns when you encounter this type of connection. And last would be a fixed support. You can also commonly see this type of support. So here we have the three unknowns. So you can't move it along X. So there is a support reaction. You can't move it along Y. So there is also a support reaction. And you can't rotate it. So that's why there is also a couple moment. So these are your three unknowns when you encounter this fixed support. Okay, so either you memorize all of that or you just try to remember the two general rules for establishing support reactions. So that is if they prevent translation and if they prevent rotation in a certain direction, then it means there is a support reaction there. So this is the first step in drawing our free body diagram, and we will be doing a lot of this in our next lesson, which is about structural analysis. So you need to familiarize yourself with these types of support reactions. Okay, going to internal forces. So in our structural analysis, first we will be identifying external support reactions and as well as the external forces applied to our rigid body. But when we arrive at like the method called method of sections in structural analysis, we must also know about internal forces. So these forces are occur in collinear pairs. So they have the same magnitude and opposite directions when you try to cut this body and analyze the internal forces. So since these forces cancel each other, they will not create any external effect in the body. Okay. So unless you try to cut a cross section of the rigid body and analyze it, then you will just need to take account of the internal forces. But if we're dealing with the whole rigid body, then the internal forces would have no external effect on the body. Okay, this is one sample problem where, as you can see, we have a beam here and we have some perpendicular trusses that is attached to it. So in the front view, this purlins, these are called purlins, will be exerting a force on our beam in such a way. This, we have force F here applied on this part of the beam, another force in this part, and another force on this part. And as you can see, this is pin connected at A, and this is roller connected at B. So for a simple exercise, we will identify the support reactions. So without going back to our what do we call it, a cheat code or cheat sheet for our identifying our external reactions. So how many support reactions are there when we have a pin connection? So there should be, so our beam cannot move along X, so that's why we can say that there is an external reaction. Let's say this is FA, so let's call it FAX. Okay, and there is no movement along Y, that's why we will also. So now, how do we know the direction of our force? So this is just an assumption, okay? So first, I will assume that the external reaction is compression towards this joint A here. So let's call it F A Y. So the general idea is that the summation of all the forces along X and along Y must be equal to 0. So if all of these forces are going, if we will draw an X and Y axis here, this is X, this is Y, this is negative X, and this is negative Y. you can see all the forces here are going negative y. This is negative, this is also negative, and this is negative. So the logical assumption to do is that this FAY should be going up or is positive. Should be positive. Why? You cannot get a zero summation if all your forces are negative. Okay, so how about B? How many external reactions do we have? This is a roller. It means the beam can move freely on the X axis. That's why there is no support reaction. It cannot move along Y. That's why we will put reaction FBY. Which is also going up. So how did we come up with such an assumption? Okay, so for that, it depends on the magnitude of each of these forces along Y. But another check would be if you will do a summation moments. So our condition for equilibrium of a rigid body is that the summation of forces should be equal to 0 and the summation of moments should also be equal to 0. So let's see here, if we do a summation moments in along or on joint A, it should be equal to 0. So what are the moments? So we will have this force F times A, which will rotate it clockwise. Another force F times A plus B will rotate it also clockwise. And another force F times A plus B plus C, which will also rotate it clockwise. So how can you achieve a summation moments which is equal to 0 for using FBY? That is, FBY should make a moment about point A, which is, since these three are clockwise, FBY, the moment created by force BY should be opposite that or anti-clockwise. So it just makes sense that it should be a positive force and it's going up. Okay, so that's our explanation for how we draw our assumptions about the sense or the direction of each support reaction. Okay, so another sample, draw the free body diagram of the uniform beam shown. So the beam has a mass of 100 kilograms. Okay, so what do we need here? So most of the problems, sometimes they will tell you to neglect the mass, but this one, or neglect the weight of the beam, but this one, it's not stated as that, and the mass is given. It means we should include this on our free body diagram. So how? So along the 6-meter beam, where should we apply the weight of the beam? So the weight must be equal to the mass times gravity. So that's 100 times 100 kilograms mass times 9.81 meter per second squared. That will give us newtons. So it means it's 981. So we will put it somewhere on it should be applied on the centroid or the center of gravity of the beam. In this case, that would be 3 meters from point A. So we have here 3 meters. So the weight of this beam would be applied here, and that is equal to 981 kilogram meter per second squared, that is Newton. Okay, so now that we have placed the weight of the beam, we also have here a 1200 Newton force applied somewhere here 2 meters from point A. Okay, so what is this? it's a fixed support. So how many unknowns when we have fixed support? That would be 3 unknowns. So since the two forces here are going down, I will assume that the y component here would be going up. So you can assume it to be going down as well, but the calculation will prove you wrong, and you will just reverse your assumption. So here, let's call it FAY. Okay, so that's FAY. And we also have, what else do we have? We also have another support reaction would be along the x component, which is FAX. And the third unknown would be a couple moment. So how will we assume the direction of this couple moment, whether it's clockwise or counterclockwise? Just do a summation of moments, let's say point A. So this moment here, 1200 newtons times 2 meters, will rotate it by clockwise. And this 981 newtons times 3 meters will also rotate it clockwise. So it's safe to say that our couple moment here, which the resultant couple moment at A, would be counterclockwise. So let's call it moment at A. Okay, so the only thing to do here is to draw the free body diagram of this uniform beam, and now we have it. So we already accounted for all external forces, its weight, and also the reactions at the support A, which is a fixed support. Now we have another one. So here is a sample problem. It wants us to determine the horizontal and vertical components of the reaction on the beam caused by the pin. So it's somewhat blurred here, but it's said that B is a pin connection and A is a rocker connection. Okay, so for this problem, it asked us to neglect the weight of the beam. So the first step for solving this problem should be to write our given. So our given includes all the unknowns and the free body diagram. So this is the beam. Now we draw a free body diagram of it, free of its surroundings, and identify the external support reaction. So it is said that joint A is a rocker connection, therefore it will have only a normal force, which is the reaction. Let's call it FAY. And point B is a hinge or pin connection, so it will have an X and Y reaction, FBY and FBX right here. So now let's discuss how do we assign the sense, or how do we assume that you must remember that since these are all unknowns, their sense or their direction are still an assumption, but how do we do a correct assumption? So let's say if we do a summation of forces just in our minds along the x-axis, what are the forces involved? We have here it is also the 600 newtons here is resolved into its components along the y and along the x. So this is 600 sine 45 and 600 cosine 45. So we have one x component which is 600 cosine 45, and it's going to the positive x direction. So it's just, if you want equilibrium, if you want them to cancel out, it just means that we should assume the unknown FBX to be going opposite that direction, since there are only two forces. Okay, So we can confirm here that the sense of fbx that we have assumed is already correct. So now, what about fay and fby? How can we make sense of it? So if we do a summation of moments on joint B right here, this joint, let's say this is our pivot point. Let's do a summation moments there. So 200 newtons will have no effect on it. FBY will have no effect on it. And FBX will also have no effect on it. So what will have effect? Turning effect or a moment. 100 newtons here. It will turn it anti-clockwise. The 600 newtons here, if we will take it here and find the perpendicular distance, something like this, of point B, it will also turn it what? Also counterclockwise. What is the remaining force? It's FAY. So the remaining force, FAY, should oppose the counterclockwise rotation since two of these forces are going to rotate point B counterclockwise. So we need FAY to turn point B clockwise. So it's safe to assume that it is going up, so that the moment its effect on point B should be a clockwise moment. So right now we can also say that the assumption for FAY is already correct. So again, it's okay if your assumption is on the other direction. Later on you will just get a negative value and you just need to reverse your assumption in order to get the correct sense of your force. What about FBY? So if we do a summation moment in A, right here, this point, take note, we're not doing any calculations yet. We're just trying to establish the sense of our external reactions, the assumptions. Okay, so 600 newtons will turn it. If we take this perpendicular distance here, it will turn it counterclockwise. 100 newtons will turn it counterclockwise as well. Clockwise. 200 newtons will turn it clockwise as well. So FBY should turn it counterclockwise. So we can say that assumption for FBY is already correct. Okay, now that you have drawn this, what is our required? We need to find FAY, FBY, and FBX all in blue. And how will we do that? We will do that by using our equilibrium equations. So this beam should not be moving. That's why the summation of the forces X and Y and the summation of the moments must all be equal to 0. So if you can recall, we already mentioned earlier that the summation forces in X only comprise of two forces. So this would be the easiest one. So we should equate it to 0, and this is 600 cosine 45. So that's approximately 424.26 newtons. That's positive since it's going right here. So we will use the positive and negative. This is positive X, this is positive Y. So the opposite would be negative. So for this, FBX would be negative X. So that's negative FBX. Okay, so this is an equation with one unknown. 0 is equal to this, and FBX, we just need to transpose FBX to the left side of the equation, and we can write it as FBX is equal to 424.26 newtons. Okay, we already identified one unknown. So the next unknown would be either FAY and FAB. FAY and FBY. So how will we find it? first is let's do a summation moments at point B. So again, why do we select point B? Because we want to cancel as much force as we can. So if we do a moment summation at point B, we already cancel 3 forces. If you can recall our lesson about principles of moments, if the force intersects the point, it will have no turning effect on that point. So when you want to select a pivot point, try to select the point wherein you will cancel a lot of forces. If we select point A, we can only cancel one force. So let's go for point B. Okay, so summation po, so let's write here the summation of moments at point B. I would like to assume that the counterclockwise moments are positive. Okay, so you can assume the opposite, doesn't matter as long as you stick with it. Okay, so we will do a summation moments at point B wherein the counterclockwise moments are positive. So let's identify which are the counterclockwise moments. So 0 must be equal to, we have there 100 newtons that will turn the B counterclockwise, so it's positive. We have 100 newtons times 2 meters. What else? We have the component of 600 newtons here, which is 424.26. It will also turn point B counterclockwise, so it's positive. So that's 424.26 newtons times 2 plus 3, that's 5 meters. What else? Okay, so there are no more counterclockwise moments. So let's go to the clockwise moments. So we have here, as you can see, notice here, the 600 Newton force is applied at this point of the beam. And we have a dimension here given as 0.2 meters. So this is 0.2 meters. So it means that we have a perpendicular distance here between point B and the x component of 600 newtons. It means it doesn't intersect B. It means it will have a tendency to rotate B, or a moment at B. And that tendency to rotate will rotate it clockwise. So we have this is negative 424.26 newtons times 0.2. So it's safe to say that we can just do this as 500 meters minus 0.2, right? So can you follow that? Since you will have minus, we just factored it out. We have minus 424.26 newtons right here times 0.2 meters. So since they are the same with this, we can factor out and just subtract that from 5 meters. Okay, so I hope you can follow that. Just pause the video and analyze it, and you will realize that it's true. Okay, the next one would be the moment that is generated by FAY, which has a moment arm of 2 plus 3 plus 2, that's 7 meters. So let me write here minus 7 times, this is 7 meters times FAY. So now we only have one unknown. If we manipulate this equation, we can find FAY. So this is 100 newtons times 2. So we transpose FAY on the other side, and we add all of this and divide it by 7. Okay, so I hope I don't need to break down the algebra in this, and you can follow it. So we will have, this is sine 45 times 600 times 5 minus 0.2 oops, let's that's sine 45 times 600 times 5 minus 0.2 or 4.8 plus 200 Newton meter. So the unit for the moment is Newton meter. And we will divide all of that by 7 and we will get 319 point this is approximate value 0.5. This is in Newton. So that is our answer for FAY. So now how will we do the last one, that is FBY? Do we need to do a moment summation? So that would be a long process. Actually, we can also do that, but it is easier to do it by doing a summation in Y. Summation forces in Y must be equal to 0. Since the only unknown left in Y is FBY. Again, we will follow the convention of the Cartesian coordinate plane. Y going up is positive, Y going down is negative. So 0 would be equal to, what are the Y components going up? We have, of course, we have FBY. We also have FAY, which is, we already solved this at 319.5. Those are only the two forces going up, so the rest are negative going down. So we have 200 newtons, we have negative 100 newtons, and we have the Y component of 600 newtons here, which is 424.26 newtons. Therefore, we manipulate this equation and solve for FBY. We get FBY as so 200 plus 100 plus 424.26 minus FAY. So let's plug that in our calculator, and plus 300 minus, we have approximately 404.77. So let me do that again. 424.26 plus 300 minus 319.5. Okay, that's 404.77. So I'm not when I'm plugging in the calculator, I'm saving values. I'm not rounding off. That's why maybe you will get a different final answer if you are rounding in between. So I am not rounding in between, that's why these are the results. Okay, so you just need to compile that into section 4 for the answers. And as you can see, all of our solved values are positive. That means it means that our assumptions are correct. So FBX is going to this direction, FBY is going up, and FAY is also going up. Okay, so don't forget to write the direction like this. Okay, and that's how you solve rigid body equilibrium problem. So let's have another sample problem. So this member or beam is pin connected at A. So pin connection, 2 reactions, and rests against a smooth support at B. So smooth support, that would be 1 reaction. So determine the horizontal and vertical components of reaction at pin A. So this is how the free body diagram will look like. So at B, it's a smooth contact, so there is a reaction which is perpendicular to the point of contact, such as this, and we'll call it in sub B. A is pin supported, so there are two reactions, FAY and FAX. As you can see, we have a distributed load, and this is the distributed load forms a triangle. So if you will compute for this distributed load at 80 newtons at the maximum, that would be 80 times 1.5, that's 120, divided by 2, that's 1/2 base times height, solving for the area of this, and that gives us 60 newtons, and it's applied on the centroid of the triangle, which is 1/3 from the from this side, and this is 1.5, so it means that it's 0.5 from this right side, and 1 meter from point A. Okay, so we still have the couple moment here rotating clockwise, 19 newton meter, and that's the free body diagram for our example. So what is required? We need to look for FAX and FAY, the reactions at point A. So our solution will start with doing a summation of the moments. Should be equal to 0. So let's take the moment at point A so that we can cancel out more forces, like this one, FAX and FAY. So we will be solving for this too later on using other equilibrium equation. So this is the summation moments at point A, joint A, assuming that the counterclockwise moments are positive, should be equal to 0. So take note, counterclockwise moments are positive. So 0 would be if this is our pivot point. So what forces will rotate it counterclockwise? We have here force NB. So NB, what will it do? So it has a moment arm of 0.75. So let's write NB times the moment arm is 0.75 meters. And I think that's the only force that will turn it counterclockwise. So let's go to the moments, negative moments. So we have 60 newtons, it will turn clockwise, so it's negative. So we have 60 newtons times, that's 1 meter. And of course you have this couple moment, 90 newton meter. So again, the couple moment, as we've learned from our previous lessons, is a free vector. That's why you can just put it anywhere, and you can write it as 90 newton meter, and that is negative since it's clockwise. Okay, so for this equation we can solve for NB. So we just transpose NB, we just manipulate this equation, we transpose the negative values on the left side, and we will get NB is equal to, that would be 60 newton meter plus 90 newton meter divided by 0.75. So 60 plus 90 divided by 0.75, that gives us NB has got the value of 200 newtons. So the reaction at B is 200 newtons, but we are looking for the reaction at point A, forces AX and AY. So what do we need to do? It's easier to find AX since we just need to do a summation forces X. So let's do a summation forces x. So summation forces in the x should be equal to 0. So we only have two components, so 0 is equal to the positive x is fax, and the negative one is the, if you can put here, the x component of NB. And if this is 30 degrees, this is also 30 degrees right here. Okay, so that is opposite the 30 degrees, so that's sine. So this is minus NB, which is 200 newtons, sine 30 degrees. So sine 30 degrees is half. So it means this is, we just transpose sine 30 degrees, this also got newtons. So manipulating this, we can solve for fax as 100 newtons. So this is 100 newtons. Don't forget the direction of fax. Since we arrive in the positive value, it means that our assumption is correct. So this is going to the right. So what remains is fay, and we just need to do a summation forces in the y direction, also equal to 0. So this is 0. So all forces going up is positive, all forces going down is negative. So this is, we have one force going up, which is fay. So for me, I prefer to list first the positive values. So it doesn't matter if you want to list the negative values first, you will still arrive at the same answer. So we have a negative 60 newtons, this one, and the y component of NB, which is, the y component is adjacent 30, so that's cosine. That is negative 200 cosine 30 degrees. And manipulating this equation, we get fay equals 60 plus, so we transpose everything to the left, so that's 60, and 200 times the cosine of 30. So we got 233, approximately 233.21 newtons, and it is going up. So it's positive, so it means our assumption is correct. So these are our answers. So just compile it on section number 4 again, but for now I will just encircle it. Okay, so that's how you please familiarize with the methods that we are doing here, because on the preceding topics we will be also employing the same techniques, although we will be dealing with trusses. These are beams, but the same analogy of the reactions and the external forces, the same treatment would be applied there. So our next topic would be about structural analysis. So our chapter objectives is to determine forces in members of a truss using two methods, the method of joints and the method of sections. So for this lesson we will just be covering method of joints, and next lesson would be about method of sections. Also to analyze forces acting on the members of frames and machines composed of pin connected members. So let's define what is a truss. So it's a structure composed of slender members joined together at their endpoints. So the members commonly used in construction consist of wooden struts or metal bars. So if you are familiar with roofing, you can see the triangular shapes in there. Those are your trusses. And you can also see these trusses in the bridges. So here, this is your truss, the front view one. This is a perspective view, and you can see that there are also purlins in the roof. So if we will take the front view, the purlins, the weight that is carried by the purlins is transferred to the joints of the truss, this particular roof truss. So all the loadings are at the joints. Another one is a bridge truss, where you have a floor beam. So from the weight distributed to the floor beam, it is transmitted to the stringers. Oh, sorry, it's the other way around. The weight of the in the bridge is transferred to the stringers, and to the stringer, from the stringer to the floor beam, and the floor beams are connected to the joints of the bridge. So for this bridge, the side view looks like this. Okay, so again, the forces are applied at the joints of the truss. Okay, so this is the explanation for that bridge truss. Okay, so let's establish first the assumptions in our structural analysis. So first assumption is all the loadings are applied at the joints. Okay, so we have seen before from the bridge, from the roof truss, the weight carried by the purlins is transferred to the joints of the roof truss as well as the bridge truss. So the weight of the member is also often neglected. Okay, so we'll be dealing with external forces only. Number 2 assumption, the members are joined together by smooth pins. Okay, so by smooth, it means there is no friction in there. But in reality, we use a gusset plate or a bolted connection such as this. So this, if you have time and you want to inspect some bridges, you can see that the connection is such a gusset plate. But in our analysis here, we will just assume that they are connected by smooth pins. Okay, more assumptions. So each truss member will act as a two force member. Okay, so the forces are only applied at their ends along their axis. So the tensile force is if the force tends to elongate the member, and the compressive force if the force tends to shorten the member. So this is the illustration. So these are our assumption that each member of the truss is acted upon by two forces. It's a two force member. Okay, either tensile force, or compression or compressive force. So a simple truss example is shown here. So it's pin connected at A and roller connected at B, and there's an external force P exerted on it, and this is your simple truss. Again, this is also another simple truss, so there is just an additional member here. Now let's go to the method of joints. So the method of joints says that if the entire truss is in equilibrium, static equilibrium, then each of its joints is also in equilibrium. If you recall what we have done with the beams from our previous topic, so we will extend that analogy to trusses. Okay, so we'll be using the equilibrium equations as well in here, and the same analysis for determining the support reactions. That's why we went through that first before this structural analysis. So each joint is subjected to a coplanar and concurrent force system. So we assume that the forces are coplanar in the same plane and they are intersecting. They are congruent force system. So let's try our method of joints for the simple truss. So what do we have here? We have a 500 Newton external force applied at B. We have here, this is a hinge or a pin connection, and this is a rocker connection. So according to our previous lesson, if this is 500 newtons going to the right, the reaction at A should be going to the, so let's call it AX, should be going to the left. So what do we have? What else do we have? We can do a summation moments in A to know what is the sense of the rocker connection in C. So summation moments, we have a moment at 500 newtons times 2 meters, which turns it clockwise. So it's necessary for the rocker connection at C, let's call it CY, to be going up. Okay, and if we do a summation moment Y, a summation force is Y, since CY is going up, the AY should be going down. So we put here AY. Okay, so if we are to determine the values for AX and AY and CY, we can do so by first doing a summation forces in X. So if summation forces in X would be equal to 0, it means that AX would just be equal to 500 newtons. So if you can follow that, just pause the video and analyze it and try to get some paper and solve for it. Okay, so if we already found out the reaction in AX. So AX is equal to 500 newtons. So the next one would be, if we will do a summation forces Y, we cannot accomplish anything since both are unknowns. So we do a summation moments in A to cancel two forces. That should be equal to 0. And summation moments in A, 0, the assumption would be counterclockwise is positive. So 0 is equal to, so CY, that will give us a positive moment, 2 meters times CY minus 500 times 2 meters, that will give us a clockwise moment, so it's negative. So 500 newton meters times 2, that's 500 newtons times 2 meters. So I think we can cancel the 2 meters here, and we can conclude that CY will just be equal to 500 newtons. Okay, so if we do a summation forces in Y, that would just give us AY is equal to CY. It means AY is also 500 newtons. Okay, so that's just a quick determination of the external support reactions. So that is our first step in doing our method of joints. Now we will proceed to going joint by joint. So we will do joint A, joint B, and joint C, and apply the same equations of equilibrium. So now that we've determined the support reactions, we now proceed to the method of joints, where we go joint by joint. And as the method of joints says, if the whole truss is in equilibrium or in static equilibrium, it means that each joint is also in equilibrium, and we can apply the equilibrium equations. But this time, since we're going joint by joint, we'll be only using summation forces X and summation forces Y, no summation moments here. Okay, so what do we want to find out? The forces in each member we have member AC, AB, and member BC. So we have 3 members. We need to determine the forces there and as well as their nature, if they are tensile or compressive. So for the first joint, we have joint B, and this is joint B here, right here. And we draw a separate free body diagram for it. So this is joint B. And what do we have? We have an external force 500 newtons. We have we assume the direction of FBC to be compressing B, since the 500 newton force is going to the right. We need a force to counter it. So that's why we want the component of FBC to go to the left. And since FBC is the component of FBC is going up, we would like to assume that FAB is going down, or that is it's tensile towards B. It's pulling B apart. If you're confused how we say it's tensile or compressive, so this is the joint. If it's pulling the joint away, tends to elongate it, that's tensile. If it's toward it, it means it's compressive. It's compressing it. Okay, so using this, we also have here this. There is an angle 45 here, so it means this is also 45-degree angle. So using trigonometry, we can resolve this into components, and we can apply the summation of forces here. So let's do a summation forces along x. That would be equal to 0. So 0 is just equal to, the positive component is 500 newtons. That's 500 newtons minus the component here is, this is cosine. So FBC, it means it's FBC cosine 45 degrees. So what we do is just manipulate this equation, and we can solve for FBC as FBC would be 500 divided by cosine 45. So that's 707.11. So 707.11 newtons. And it's positive, so it means that our assumption is correct, that it is compressive towards point B. So we can write it as a compressive force. So let's use red one. So it's compression. Okay, so that's how we determine the nature of that. Okay, we have another unknown, and that is FAB, which we can solve by doing a summation forces. Let's do summation forces in y direction. That would be equal to 0. That's equal to, going up is the component of FBC, which is opposite 45, that's sine. So FBC sine 45 degrees minus FAB, which is going down. So we can, since we already have a value for FBC, we just take the sine of that, and that is equal to FAB. So FAB would be FBC, which is 707.11 newtons approximately, multiplied by the sine of 45. That gives us 500 newtons. So FAB is also equal to 500 newtons, and it's 10 to elongate point B, so it's a tensile force. So let's write T. So it's a positive value, it means that our assumption is correct. Okay, so we already solved for FAB, FBC. What is left is FAC. So we can, where can we find FAC? We can either go joint A, since there is an FAC component there, or we can do joint C, since there is also a component of FAC there. So which one do you prefer? So I prefer the easier one, which is joint A, since we have FAB, which is in tension. There is another known in here, and FAC will just be a matter of doing a summation forces in the x direction. So for that, we only have two forces, that would be FAC and 500 newtons, the external support reaction. So it also gives us that FAC would just be equal to 500 newtons, and it is a compressive force. A tensile force. Okay, so we already solved for the 3. If you want to try to check joint C for FAC, you are free to do so as well. So for joint C, you just need to do a summation forces X in here as well. So if you do a summation forces X here, that's equal to 0. So 0 is equal to the component of FBC, which is adjacent, so that's cosine. So that's FBC cosine 45 degrees minus FAC. So if you will do that, this is FBC cosine 45, 707.11 times cosine 45, that's the same as sine 45. That gives you FAC, the same thing, which is 500 newtons, and it is compression. Oh, sorry, tension. It tends to elongate joint C. Okay, so that is how you do your method of joints. You just need to be able to identify the support reactions, solve for the support reactions, and then go joint by joint and find the unknowns per member. So this is an easy one. This is a simple truss. So you just need to find three forces. But what if your truss is a complicated one? Let's say you have like 10 or 20 members, and you will need to go joint by joint. So there's another method called method of sections, and we will be discussing that on the next lesson. For now, let's have some more examples how to do your method of joints. Okay, going back to our slide. Okay, so based on our calculations, this is the these are the values of the forces for. So FAC is in tension, FAB member is also in tension, and FBC is in compression. So let's try to check that if that's correct. Okay, FBC is compression, FAC is tension, and FAC is in FAB is in tension. Okay, so it's correct. Here. So now let's proceed to example B for our method of joints example. So the task is to determine the force in each members of the truss shown here. Indicate whether the members are in tension or compression, just like what we did from the previous example A. So as you can see here, we can count that we have 1, 2, 3, 4, 5 forces. So we'll be looking, or 5 members, so we'll be looking for 5 forces. But of course, the first step would be to determine the values of the support reactions. So we have here a rocker connection, and we have a pin connection at C. At A, it's a rocker, so it means it's only a normal force. This one is an X and Y component. So to draw the free body diagram of our example, is we already determined how many unknowns we have. So first, the required would be force in each member AB, member BC, member BD, sorry, this is BD. D. We have member CD and member ED. So 5 forces in all. So we don't really need to do method of joints for each joint. We just need to determine the joints that will give values to all of this. But first of all, we need to solve for the support reactions. So how can we do it? So if we do a summation forces in X, we only have, so if we do summation forces in X equals 0, that would be only two forces. That's the 600 Newton force minus Cx. So it means that Cx would be 600 Newtons. If we do a summation forces on Y, we have two unknowns. So let's do a summation moments. Let's do summation moments in C, taking the anticlockwise or counterclockwise as positive. Should be equal to 0. So what are the forces remaining? We have 600 times 4. That would be 2400 Newton meters. What else? We have 400 times 3 plus, that's also counterclockwise, so it's positive. That's 400 times 3, that's 1200 Newton meters. And what's left is 3 plus 3 AY, that's minus 6 AY. So we can solve for AY by, we have AY is equal to, that's 2 4 plus 1 2, that would be 3 6 divided by 6, that is also 600 newtons. And if we do a summation forces in the Y direction, summation forces Y equals 0. So the forces going up are AY and nothing else. So that's minus 400 newtons, and according to our assumption here, this is minus CY. So this is 600 minus 600 newtons minus 400 newtons, that's 200 newtons minus CY. So CY is equal to negative 200 newtons, which means that our assumption is incorrect. It means it should wait, we have AY going up, we have 400 newtons going down, and we have CY going down. Okay, so it means it's a positive value, sorry. So CY is 200 newtons. Okay, now we already determined our support reactions. Now let's go to analyze it per joint. So let's go for joint A first. So we found AY here to be, let's erase it and substitute. AY is 600 newtons. So let's write 600 newtons here, so that we have two unknowns only. So for joint A, let's do the summation of forces that will give us a value. So since AY is in the Y, let's do first summation forces in the Y direction equals 0. So that would be equal to 0 equals 600 newtons is going up, and we need to determine what is this angle. So what's this angle? So this is actually a 3 4 5 triangle, as you can see here. So we can use that ratio to compute for the component of FAB in the Y direction. That would be minus 4/5. We want this ratio here, 4/5 of FAB, which means that FAB would just be equal to 5 times 600 divided by 4. So that 5 times 600 divided by 4 is 750. So FAB is 750. We have a positive value. It means we have a correct assumption. So our assumption for FAB is it's compressing A. So it's a compressive force. So now we have one force here, FAB. Let me just change the color of this one. I will put it as a blue one. Alright, so what's left? We can do a summation forces in the X to find FAD. Since we already have a value for FAB, we need to find FAB. So summation forces in X equals 0. So that 0 is equal to FAD going to the positive direction minus the component of FAB, which is 3/5 of FAB, or 3/5 of 750. So that would be 450. So color FAD will just be equal to 450. 450 newtons, and that is tensile. It tends to elongate joint A, so it's tensile. Okay, so 2 forces down, 3 to go. So let's go to joint D. So FAD is said to be tension, so the assumption for FAD here is correct. So let's not change that for now. We cannot know for sure what is the direction of FCD and FBD, so let's leave it the assumption such as this. So let's start by computing. What should we compute? We compute the first one with least unknowns. So let's go to summation forces. Now we are in joint D. Okay, this is joint D. So this is F force BD, this is force CD, this is force AD, and this is the 600 Newton external force. So let's do a summation forces in X in joint D equals 0. So 0 would be, we have a 600 Newton force. We have the FAD is negative here, so we have negative 450 newtons, and we have another negative what's this ratio again? This ratio is again a 4 3 3 4 5 triangle, so we can use that ratio to find the X component, which is 3/5 of FBD. So we can solve for FBD by transposing it to the other side and multiplying what remains by 5/3. So we have here FBD is equal to, that's 600 minus 450, that's 150 times 5 divided by 3. 150 times 5 divided by 3, that gives us 250. So this is a 250 Newton force, and it's positive, so it means our assumption is correct, and it's a tensile force. Alright, so it's tension. Okay, 3 forces. So what's next? We need to find FCD, and as you can see, we only have 2 components here, so summation forces y equals 0. So 0 is equal to, what do we have? We have the positive component of FBD, which is 4/5. So that's 4/5 FBD minus FCD. So it means we just need multiply 250 by 4/5. So that's 250 times 4 divided by 5. That's 200. So FCD will have a value of 200 newtons, and it's positive. So FCD is equal to 200 newtons positive. So it means that it is compressive. So it means our assumption is correct. So don't worry if you get a negative value, you just need to reverse your assumption. Okay. So we already have 4 forces. So we only have one BD and CD. Okay, we have what do we have left? For joint C we have BC. Okay, so we solved AD earlier, but we don't have BC yet. So now we're going for BC, and we can find that by going to joint C. We already have a value for CX, which is 600 newtons. So if we do a summation, if we do a summation forces Y, X, we can find that FBC 0 is equal to FBC minus CX, which is 600 newtons. So it's safe to say that FBC would just be equal to the same thing, 600 newtons. So if you are confused how we came up with the assumptions here, just pause the video and try to analyze how we came up with the assumptions of the directions or the sense of the forces for each joint. So 300 newtons, and this is compressive. Sorry, we should be using a different color. So that's a compressive force. Okay, so now we already found all the forces by doing the method of joints. So always remember, for doing the member of joints, first is you need to know how to compute for the support reactions. It should be correct, or else if you compute support reaction incorrectly, of course each joint would also be incorrect. So go select the joint where you can with the least unknown. Okay, so for this one you have no choice but to select joint A, since it has two unknowns. For joint C, there's also two unknowns at the beginning. For joint B, there's 3 unknowns. So we will stay away from joint B. For joint D, initially there is also 3 unknowns. We stay away from that. Okay, so you just go from joint by joint to find the unknowns that required for the problem. So I won't box this once, just take note of them. These are your answers: FAB, FBC, FAD, FBD, and FCD. These are your values. So now let's check. Okay, so this would be how our members will look like. So for AB, that is 750 compression, correct? For AD, that's 450 Newton tension, that's correct. For BC, that's compression, that's 600, that's correct. For BD, that's 250, that's tension, that's correct. but for what's this, CD 200, it's compression 200 Newton FCD. Okay, we have this is compression. Okay, so let's correct that. Okay, so it's good that you check your final answer. Okay, so that you will not have an incorrect sense. So this is AB, that's compression according to this. Yeah, that's correct. And we only have one thing that we got wrong. This one, FCD 200, but actually in the drawing it's also compression. It's just my mistake. Okay, so that's how you do your method of joints. So our source for this lecture would still be our reference book, Engineering Mechanics Statics, 14th edition by Russell Hibler, and you can find this in chapter 5 and chapter 6 from pages 207 to 281. If you want to practice more, you can study the other examples there, and if you have questions, just use our Q&A form or send me an email. So as always, thank you for your attention, and good luck.